Hi everybody, welcome to this presentation entitled From If Then Else to Deep Learning and Back. My name is Bart Baesens. I'm a professor of Big Data and Analytics at the Department of Decision Sciences and Information Management at KU Leuven. You can find my details at the bottom of the slide. In case you'd be interested, I'm more than happy to send you the slides of this presentation. A little bit of information about myself before I kick off. I studied at KU Leuven in Belgium. My master's degree was business engineering in management informatics. I obtained my PhD in applied economic sciences in 2003. It was entitled Developing Intelligent Systems for Credit Scoring Using Machine Learning Techniques. Afterwards, I zoomed out with my research and I also started doing marketing analytics, fraud analytics, churn prediction, response modeling, etc. If you want more information about my team and my research, you can have a look at my YouTube, Facebook, and Twitter accounts. I run the Data Mining Apps group, which has separate YouTube, Facebook, and Twitter pages. You can also have a look at our website. We actually issue a 2-weekly newsletter to update people about all the research that we're doing in big data and analytics. As already mentioned, you can also contact me at my email address at the bottom for more information, and I'm also happy to share the slides of this presentation in case you are interested. Here you can see some of my example publications. As you can see, together with my team, we cover a pretty broad range in big data and analytics, ranging from fraud analytics to credit risk analytics to profit-driven analytics, etc. Our most recent book is in the lower right corner. It's Principles of Database Management, which also comes with an accompanying slide decks with online quiz tools, etc. If you want more information about that, let me know, and I'm more than happy to share that with you. Here's an initiative that I recently started with a colleague Professor Tim Verdonk. It's BlueCourses. It's an online digital learning platform where we offer online courses on a variety of different topics. We currently have 5 courses online, 2 credit risk modeling courses, a basic credit risk modeling course, an advanced credit risk modeling course. We have a machine learning essentials course, which is actually quite popular at the moment. We have fraud analytics, social network analytics, and we're currently working on text analytics, a deep learning course, as well as an uplift modeling course. Part of our mission statement at BlueCourses is to not only offer online courses, but also invest in our very precious oceans by pledging to transfer 20% of our EBIT, earnings before interest and taxes, to companies cleaning up our oceans from plastic. So you actually, whilst learning, you also contribute to this purpose. In case you're interested in more information, feel free to have a look at our website, www.bluecourses.com, and you'll find more information there. Okay, so let's start with if-then-else rules. If-then-else rules were basically the first type of machine learning models that you can think of. And they were humanly engineered in the sense that the if-then-else rules were obtained from business experts using knowledge elicitation techniques. Think about a fraud investigator, for example. Fraud investigators, if they have been investigating fraud files during years and years, they have accumulated a tremendous amount of knowledge, a tremendous amount of experience that allows them to actually screen fraud files in a very efficient way. This knowledge can then be elicited from the experts using knowledge elicitation techniques and written down as if-then-else rules, right? Think about an if-then-else rule that could be, look, if there's a car accident and it was a severe accident, but no doctor came to the place, then this claim could be flagged as suspicious. This is an example of knowledge that can be very easily written down as an if-then-else rule. Those expert-based if-then-else rules are very useful, right? And they're very important, even still nowadays with the emergence of analytics. But besides rules that you have obtained from these experts, thanks to the emergence of analytics, we can also now have rules that are directly being inferred from data. There exist various analytics-based techniques that allow you to infer if-then-else rules from data. Think about decision tree algorithms such as C4.5 or its successor C5, Jade, Guard, etc. Many of these rules will actually extract confirmatory patterns from data, which were already known by the experts before, which is good because that's validation of those patterns, but they will also extract novel patterns that were not known to the experts before. And that's where data-based rules can come in very handy. It's not a battle between expert-based rules and data-based rules, but it's a way of actually reconciling both and finding the best of both worlds. There will always be expert-based rules which you will not find in data, and vice versa, you will always have database rules that were not known to the experts before. So both are actually very essential if you want to build high-performing analytical models in today's environment. Let's zoom into the database rules first by looking at the analytics process model. Here you can see the analytics process model outlined at a high level. So first you have to identify your business problem. What do you want to solve with analytics? You want to detect fraud, you want to predict churn, or you want to predict response to a marketing campaign. Once you carefully identify that, you can start identifying your data sources. And the idea there is to identify as many data sources as possible. Anything that could be potentially relevant to either predict churn, predict fraud, or predict response, you actually gather it. Right? The more the better. As soon as you think that it could potentially be relevant, you collect it. You then bring it into a staging area. You select the data, bring it into a staging area. The staging area oftentimes could be an Excel file, it could be a data mart, it could be a data warehouse. It's just an aggregated view on all data available to solve your business problem using analytics. Obviously, as we all know, this data will contain inconsistencies. It will contain noise. It will contain things like missing values, outliers, etc. It might even contain duplicate data. So you have to clean it up. That's the next step. The next step is transform the data. And transform the data often boils down to enriching the data, to making the data suitable for your analytical technique to be analyzed. And let me elaborate on one step of this data transformation activity which I consider to be very important. And that's the feature engineering step. Feature engineering is really very important. Now, what is a feature versus a data element? If you look at date of birth is a data element. Age is a feature. A feature is something that you derive from data elements. So age is a feature that has been derived from the data element date of birth. Carefully engineering those features is really important in today's analytics world. I think it's really important to carefully think about those features. Other examples of features could be historical trends. Think about a historical trend in, for example, a debt ratio. The historical evolution of debt could be very well captured by a feature, which can then be fed to a credit risk model to predict whether somebody's going to go bankrupt, yes or no, is going to default, yes or no. So feature engineering is a very important step in this transform data activity, as it will allow you to better detect analytical patterns in the subsequent step. Subsequent step is the analytical modeling. It's the machine learning. So you're going to learn a machine or a statistical model to discriminate, for example, the green dots from the red dots, as you can see in my figure, the red dots representing the fraudsters, the green dots representing the non-fraudsters. It could also learn to discriminate between the churners and the non-churners, between the responders and the non-responders. Once you've finished with the machine learning, the post-processing will start. And there you're going to actually inspect what your machine has learned, how your analytical model looks like. So you're going to start interpreting it and see whether there's some confirmatory patterns or novel patterns. Confirmatory patterns means that it's kind of reassuring, right? Suppose you have a credit risk model, and your credit risk model has learned that a higher debt ratio leads to a higher credit risk. That's what I would refer to as a confirmatory pattern, because that's what you exactly would anticipate. But besides those confirmatory patterns, you will also learn novel patterns, things that were unknown to the business expert before. And that's where analytics actually has a competitive advantage, where it can learn new behavior from data. And that's where analytics is very important. Obviously, you're also going to evaluate your analytical or machine learning models. And you can do that in various ways, as we will explain in a moment. And at the end of the day, once your machine learning model has been adequately interpreted and evaluated, it can be deployed in your business environment to score credit applications, to detect fraudulent transfers, to detect fraudulent files, etc. Here you can see some examples, right? Let's take an example of marketing analytics, churn prediction. Now, what is churn prediction? Churn prediction means that you want to predict if customers are going to leave your organization, yes or no. Churn prediction is very popular in telco to detect what clients, what customers are likely to switch to another telco provider. And you can do that using various types of data elements, but also using manually engineered features. Here you can see the recency, frequency, and monetary features. Those are features which are not readily available as such in your transactional telco data, but which you have to engineer from there. Recency means, for example, how long has it been since the customer made a phone call. You can measure that in terms of minutes, in terms of hours, in terms of days, etc. Frequency then reflects upon how often a customer calls. What's the average? Monetary can then reflect what's the average amount of the monthly bill, for example, right? Those are manually engineered features. The recency, frequency, and monetary features have been very popular in marketing analytics, not only for predicting churn, but also for customer segmentation. The recency, frequency, and monetary features have also been very popular in fraud detection, by the way, right? Because if all of a sudden, think about credit card fraud, you can also look at recency of transactions, frequency of transactions, and monetary value of transactions. And if you see transactions that start deviating from the average values, then that could signal potential fraud. So here you can see that in predicting customer churn, traditionally, people used manually engineered features. They had a binary target, and then the purpose of machine learning was to learn a statistical or a quantitative model to discriminate between the churners and the non-churners. Here we have a categorical target, churn yes or no. You can also think of a continuous target, and a continuous target is the customer lifetime value. It's the or the CLV. CLV is a concept that looks at what value a customer is likely to generate at your firm. We can never predict until infinity, so usually CLV measures are calculated using a 2-year to 3-year time window. And you can use the same manually engineered features, recency, frequency, monetary, except that now you have a continuous target instead of a categorical target. Note that these manually engineered features like recency, frequency, and monetary can be obviously augmented with other types of information as well. As I already said, the more columns you have in your data set, the more variables that you have, or the more predictors you have, the more interesting it becomes for your machine learning technique to find complex patterns. In traditional machine learning, those features, recency, frequency, and monetary, had to be manually engineered from your data. So you had to write Python scripts, you had to write R scripts to actually calculate those features from the data. Let's now have a look at some analytical or industry benchmarks. Well, if you look at many techniques in the industry, they're still based on very simple analytical models, such as linear regression or logistic regression. At the top of my slide, you can see a linear regression model for predicting customer lifetime value. So it has an intercept of 200, and then it has 3 features, recency, frequency, monetary, which each have an associated weight. For recency, the weight or regression coefficient is 5. For frequency, it's 10, and for monetary, it's 2, so as to reflect the impact on the CLV. Right? Obviously, this is just a very simple CLV model, and you can easily extend it to take into account more features or more data elements like the income of a person, like the gender of a person. We all know that gender is a very important piece of information in any analytical context, but obviously have to be careful with this piece of information in terms of discrimination, etc. So the CLV model can actually contain lots of variables. If you have a categorical target like churn or like fraud, then you could use linear regression, but it's better to use logistic regression. Logistic regression is basically a linear regression, but you put a transformation on top of it so that the outcome is always bounded between 0 and 1. And why do you want that? You want that because you want to interpret it as a probability, right? And a probability is always between 0 and 1. Linear and logistic regression have been very popular in credit scoring, right? Because there you want to have insight into what makes a customer default, yes or no. And that insight can be easily obtained from techniques such as logistic regression. Linear and logistic regression have also been very popular in medical applications because there also insight is a very important aspect. Another analytical industry benchmark is the decision tree, right? And you can see an example of a decision tree here, again illustrated with my recency, frequency, and monetary features. So we have a top node that says frequency bigger than 5, yes or no. And then depending upon the outcome of that testing condition, you either navigate down to the right or to the left where a next testing condition is being evaluated until you arrive at the leaf nodes where a classification is being made. Here you can see the classification, churn, no churn. Could also be default, non-default, or fraudster, non-fraudster. Decision trees are very popular, obviously. Why? Because they're very interpretable, right? They give you those if-then rules, but now learn from data. So earlier on we spoke about data-based if-then rules. Here you can see how decision trees can very easily give you those data-based if-then rules because this decision tree has 4 leaf nodes, so it can be equivalently represented using 4 if-then rules. One of them being, for example, if frequency is bigger than 5, yes, and recency is less than 2, no, then churn, then the customer is a churner. Decision trees have been very popular in credit scoring during pre-processing, for example, to categorize variables or also to do some initial segmentation. They've also been very useful in churn prediction to predict if customers are going to leave your organization, yes or no. Linear, logistic, and decision trees are very basic machine learning techniques. Neural networks are a little bit more complicated, and a neural network works using neurons. And here you can see a neuron represented. So here you can see a neuron that has 3 inputs, recency, frequency, and monetary, and it has a 4th input at the bottom, which is fixed to 1. This neuron is going to do some internal computations, which we're going to zoom into in a moment, and is going to give an output, right? That's what a neuron does. It takes inputs, it takes various inputs, and it yields an output. And it does an internal calculation, an internal computation. But what type of internal calculation or computation is it doing? Well, let's have a look. Here you can see the internal anatomy of a neuron. So we again have those inputs, recency, frequency, and monetary. And one of the inputs we always fix to 1. This corresponds to the intercept in the linear regression. So you have this intercept term in linear regression, often denoted by beta 0, which is the value of your target in case all your variables have, all your predictors have a value of 0. So it's like a fixed impact on your output. And we have a similar term here in this neural model. Now each of the inputs has weights associated with it, and then a neuron is going to perform 2 types of activities. First, it's going to take the sum the weighted sum of its inputs, right? So in our particular case, this will be recency times W1 plus frequency times W2 plus monetary times W3 plus 1 times W4. It takes that sum and is then going to feed that sum to what we call a transformation function, right? transformation function, sometimes also referred to as an activation function, squeezing function, and etc. And some popular examples are a sigmoid transformation, hyperbolic tangent, exponential, linear, real-loose, etc. And that transformation will then give us the output of that neuron. That's how one neuron works. Now, you can imagine that one neuron is very powerful, but if you start combining them, if you start adding more and more of them, then you can get very powerful analytical or machine learning models. And that's the idea of neural networks. So here again, we have our input layer with three features: recency, frequency, monetary. We can add as many as we like, right? And then we arrange all those neurons into layers. So we have a hidden layer, in this particular case, with 3 hidden neurons. You can see at the bottom of each neuron, you can see that there's like the arrow coming in, which represents our intercept, or as they would refer to it in the neural network setting, bias term. So this hidden layer then gives us outputs which are being combined in the output layer and gives us the final output measure of interest, which could be a churn score, which could be a fraud score, response score, or in our case, the customer lifetime value. Obviously, all these connections have weights associated with them, and one of the tricky things will be to find those appropriate values for these weights. This is something that you typically do during a learning step, during a learning procedure, using stochastic gradient descent-based methods such as backpropagation. Now let's have a look at this hidden layer. Basically what this hidden layer does is it's going to learn representations, combinations of the input features, which it then feeds to the output layer to predict as good as possible the CLV or the churn. So basically, if you think carefully about it, this hidden layer is a feature learner. It learns features. The top hidden neuron, for example, could focus on a particular combination of recency and frequency, which it then feeds to the output layer. The middle hidden neuron could focus on a particular transformation of frequency alone. And the bottom neuron could then focus on maybe a combination of recency, frequency, and monetary. Again, another feature which it feeds to the output layer. So the hidden layer can be thought of as a feature learner. So rather than manually engineering the features as we did before, think about the recency, frequency, and monetary example, we now automatically learn features from data, which is the nice thing about neural networks. Right? A not so nice thing about neural networks is that the complexity is pretty high, right? Because here we have a hidden layer with only 3 hidden neurons, but you can add more of those hidden neurons to your hidden layer. And the more hidden neurons you add, the more complex your neural network becomes, but which also has an advantage because then you can learn more complex patterns from your data. So you can see that neural networks in that hidden layer, they kind of automatically learn features from data. Neural networks with only one single hidden layer are often referred to as shallow neural networks. Think of it as very compact neural networks. And as already mentioned, the hidden layer automatically extracts features from the data. The features are now automatically learned by the network instead of the manually engineered features like the RFM features that we have discussed before. However, computational requirements remain a little bit of a concern because you have a lot more parameters to estimate. So the estimation of the model, though this is less of a concern these days, but the estimation of the model is more time consuming than the estimation of a classical linear regression, logistic regression, or decision trees. Neural networks are often referred to as black box models because they kind of relate the input to the output in a nonlinear black box way, using, in other words, a very complex mathematical formula. You can work out the mathematical formula relating to the outputs. They're relating the outputs to the inputs in. You can do that. You can write it down as a mathematical formula in a pretty straightforward way, but the formula itself looks very complicated. Right? So that's why neural networks have been used in application settings in areas where interpretability is less of a concern. Suppose you're only interested in detecting whether a transaction is fraudulent, yes or no, but you're not that much interested in fraud prevention in the sense that you don't want to understand the patterns behind it. You just want to label transactions as fraudulent, yes or no. then neural networks have been very successful for this purpose. They've also been very successful for response modeling. The idea of response modeling is to predict if somebody's going to respond to a marketing campaign, yes or no. And in those settings, typically you don't care why they respond. You just want to know if they will respond, yes or no. So black box models like neural networks suffice in those kind of settings. Neural networks have also been successfully used in forecasting, for example, to analyze time series data. Before we continue a bit further and move towards deep learning, let's have a look at some evaluation criteria which are commonly adopted if you work in analytics. The first one is obviously accuracy. Suppose you're predicting churn. If you're predicting churn, then you want to predict churn as accurately as possible. You want to discriminate the churners from the non-churners as accurately as possible. Likewise, if you predict CLV, you want to predict the CLV as accurately as possible, right? So accuracy is a very important KPI, key performance indicator of any analytical model, right? And it's usually measured in various ways, depending upon what you want to do. Suppose you want to predict churn, then you can measure accuracy using lift curves, using receiver operating characteristic curves, looking at top decile lift, etc. If you have a continuous target, like if you want to predict CLV, you can look at mean squared errors, mean absolute deviations, Pearson correlations, etc. Accuracy is a very important analytical evaluation criterion, but it's not the only one. Interpretability is also very important. In credit scoring, for example, you want to understand why customers default. Actually, you are legally required to explain why you are denying credit to a particular customer. That's why interpretability, understanding how your credit scoring models work, is very important. Operational efficiency is also very important. If you want to do online real-time scoring, you want to have your score as quickly as possible. If you do credit card fraud detection, typically you only have a few seconds to block a transaction, yes or no. In one of the projects we did, we had 8 seconds to block a transaction, yes or no. So you better make sure that your analytical model is capable of gathering all the data, of pre-processing it, of engineering the features, and then making the decision whether a transaction is fraudulent, yes or no, within those 8 seconds. So that would mean, actually, that sometimes you would have to sacrifice a little bit of accuracy in return for operational efficiency. And the fourth criterion is economical cost. And that's the cost, that's the economic perspective. The cost of using the model. Not only the cost of using the model, but also the cost of developing the model, but also the cost of model errors, right? If your analytical model labels a fraudster as a non-fraudster, right? What is the cost or versus labeling a non-fraudster as a fraudster? There's clear asymmetry in the costs. So that's a fourth evaluation criterion that has to be taken into account. And we've recently done some research on that, like we've developed an extension of logistic regression, which rather than optimizing a likelihood function, optimizes profit. We have developed an extension of decision trees, prof-tree, that instead of maximizing purity or minimizing impurity, directly optimizes profit. And we've also developed an extension, prof-arima, that builds ARIMA models in a profit-driven way for time series forecasting. Now, one spoiler alert already is that deep learning predominantly focuses on the accuracy, right? And less on the other aspects. Before we go a little bit further into deep learning, let's make sure that we appropriately understand the characteristics of the techniques we've discussed thus far in terms of these analytical evaluation criteria of performance, interpretability, operational efficiency, and economical cost. Linear and logistic regression score good on all these four criteria. So they give good performance, good interpretability, good operational efficiency, and good economical cost. Decision trees give better performance than usually linear and logistic regression, better interpretability, same operational efficiency, same economical cost. Neural networks give excellent performance. They're capable of actually learning very complex patterns from data. Why? Well, remember, because of this universal approximation property. A neural network with one hidden layer can approximate any function to any desired degree of accuracy over a compact interval as long as you feed it with enough hidden neurons in that hidden layer. However, neural networks are clearly inferior in terms of interpretability, right? It's a two-edged sword because they are capable to learn more complex patterns, but it comes at a cost of interpretability. Operational efficiency is also an issue, although with nowadays maybe less of a concern, but because of all the transformations that take place, because of the complexity, obviously your operational efficiency might suffer as well. And the economical cost of neural networks is also a downside. We can back up these claims with various benchmarking studies that we've done, and I've referred some of them at the bottom of my slide in case you would be interested. Now, I already briefly referred to it, but when you deploy analytical models, you have a difference between white box applications and black box applications. White box applications are applications where you want clear insight into the patterns in your data. You want to know what happens in your data and why your analytical model makes a certain decision, yes or no. Credit scoring is one of the most popular examples of a white box setting. Because of recent regulation, such as Basel and IFRS 9, credit scoring models must be white box. So you cannot go to a bank and get credit scored and then get a loan rejected because of a neural network, because neural networks are black box models. So that's why the number one credit scoring technique used by banks worldwide is logistic regression. It's easy to understand, and as a side remark, it works really good in credit scoring. Also for medical diagnosis, the FDA, Federal Drug Administration Authority, kind of enforces pharmaceutical firms to use white box models like linear logistic regression and decision trees because it gives you the key insights of what is happening in your data. If you want to do fraud detection and prevention, it's very important that you understand the fraud mechanisms. Neural networks will not facilitate understanding of the fraud mechanisms, so that's why we again need to resort to simple techniques. Note, however, that there are areas in which black box applications are perfectly legit. As already said, response modeling is one of them. If you only want to model if a customer is responding to a marketing campaign, yes or not, and you're not that much interested in the why, then just use a neural network. It will work fine, it will work good. Image analytics, text analytics, these are what I would refer to as analytics on unstructured data. Now here's an important term, unstructured versus structured data. Unstructured data, let's first explain structured data. Structured data is data that can be easily structured in a tabular format. In a tabular format, think about an Excel file, for example, which is essentially a tabular format, has rows and columns. Unstructured data cannot be structured in a tabular format in an easy way. So in those application areas where you have unstructured data, such as image analytics or text analytics, where you want to do clustering, categorization, etc., black box models are very good techniques to analyze these types of data. What were the deep learning triggers? What kind of triggered the interest and the popularity of deep learning? The emergence of graphical processing units and tensor processing units, parallel computing, cloud computing, NoSQL databases, think about MongoDB, Neo4j, etc., that facilitated the storage of unstructured data, but also the software, the emergence of very powerful software. You can see some software suites listed right there, TensorFlow, Keras, Caffe, etc., which kind of allowed us to build very complex models. Right? Deep learning is a very complex analytical model that kind of looks like this. It's basically a very simple, maybe somewhat naive definition of a neural network is a multi-layer neural network, or of a deep learning model is a multi-layer neural network. So here you can see a neural network that not only has one hidden layer, but you're going to add more and more hidden layers to your neural network. That's what we call a deep learning neural network. So we no longer have a shallow neural network, which only had one hidden layer, remember, and also had that universal approximation property, but we're now going to add more hidden layers to the neural networks. And the hidden layers can be connected in various ways. But essentially, a deep learning model is a multi-layer neural network. Again, you have your input layer with your inputs, you have various hidden layers connected in particular ways, and you have your output layer that actually is going to give you the output measure of interest. That's in a very basic nutshell how a deep learning model works. Various applications we have seen of deep learning, and most of the applications work on unstructured data. Remember what I said earlier, that unstructured data is data that cannot be easily represented in a tabular format. Image analytics is one of them, audio, video analytics, textual analytics, recommender systems, music generation, gaming, etc. Right? Let's briefly discuss a few examples, maybe like image coloring. So I read a lot of books and I watch a lot of videos on World War I and World War II. Now, many of those movies and videos are still black and white colored. So you can use a deep learning neural network to start from a set of images and to kind of color those black and white images using modern day colors, right? That's one example, image coloring. Or image captioning. You can feed an image to a deep learning neural network, and then the deep learning neural network will actually learn what's represented in the image. So in the upper right corner of my slide, you can see that the deep learning neural network can learn that there's a black and white dog that jumps over the bar. Very powerful applications. The deep learning bit related, a deep learning model can also help in object detection. In the lower left corner, you can see various objects. You can see an elephant. You can see a man sitting on the elephant. You can see a soccer ball. These are all things that the deep learning neural network can learn from you. Deep learning can also help you translate text from images and so on. So it's really good at processing unstructured data and generating knowledge from there. Those deep learning neural networks, as I already mentioned, they are, in essence, they're multi-layer perceptual neural networks, but the connections between the various layers and the transformation functions used in those layers, used in those neurons, can be tailored to the problem at hand, right? Convolutional neural networks are one type of neural networks that are very good at analyzing images, for example, right? And they work with different convolution and pooling operators, different types of connections to start from an image like you see at the top of my slide and to see what is in that image. Here you can see that your deep learning neural network has learned that there's a boat in the image, because you can see at the right of the neural network that the probabilities of a boat appearing in there are 94%, which clearly indicates that it's likely that there's a boat in the image. So this is a deep learning neural network. It can be used in a variety of ways to actually learn patterns from unstructured data. One way that we've also seen it being used is to match, for example, CVs, curriculum vitae, which actually describe what you've accomplished in your life, with job descriptions. Again, two types of unstructured data, in this particular case, textual data, that you can very much relate with each other in a mathematical or machine learning based way using deep learning. I mean, every now and then you also see some funny stories popping up. Like here you have the US Army wanted to use neural networks, deep learning alike neural networks, to automatically detect camouflage enemy tanks. You'll see that oftentimes, I've collaborated a bit with defense with countries worldwide. You will see that oftentimes the most sophisticated analytical models have been deployed for defense purposes. But here it turned out not to be that sophisticated, because the US Army trained a neural network on 50 photos of camouflage tanks in trees and 50 photos of trees without tanks. First of all, 100 photos total training set is not a lot to train a neural network with. It's highly recommended to have at least a few thousands of observations to train your neural networks if you want to do it in a decent way. Apparently, even with the small data set, the neural network classified all test set photos 100% correctly. However, it turned out that in the data set, photos of camouflage tanks had been taken on cloudy days, while photos of plain forest had been taken on sunny days. Right? So the neural network did not discriminate between camouflaged enemy tanks and something else, but it had learned to distinguish cloudy days from sunny days instead of distinguishing those camouflaged tanks from empty forests, which is actually not a good thing. Now, deep learning, as I said, are in essence very complex techniques, right? They're multi-layer neural networks. But what if you want to add the interpretability layer on top of that? Well, if you want to add the interpretability layer on top of a neural network, one way to accomplish this, and there exist various ways, you may have heard of Lime and Shapley ways. We discussed those in our BlueCourses course on machine learning in case you'd be interested. So Lime and Shapley are definitely already one way of shedding some light on what's happening in a neural network. But another way is by extracting rules from the neural network, by going back to those if-then rules that we kind of started this presentation with. So remember that we had those if-then rules that came from either from experts or from the data. Well, we can now also get it from our deep learning models by actually engineering the deep learning neural network in a careful and intelligent way and extracting rules out of it that mimic the behavior of our deep learning model. This is something that I studied in my PhD already in 2003. The idea was to start from a neural network because it's a powerful model. It allows to learn very complex patterns from your data and then extract rules that mimic the reasoning of your neural network. It's a kind of best of both worlds approach. You try to combine the power of your neural network, the performance, with the if-then rules. Here you can see an idea, here you can see an example. It's from my PhD, so it's a very simple neural network, but the methods that we discussed in my PhD, and which we also extensively discuss in our BlueCourses course on machine learning, generalized to any type of neural network with any number of hidden neurons and any number of hidden layers with hidden neurons. So you can see that you have a neural network that to the left has various inputs. We can see the weights. We can see it has one hidden layer with two hidden neurons, and the output layer has two neurons to decide whether the applicant is good or bad, right? And then we try to extract if-then rules, and there exist various ways to do that. There exist pedagogical techniques, but also decompositional approaches that allow you to extract if-then rules. Again, if you want more information on this, I refer to our BlueCourses course on machine learning. But here you can see a rule set, and this rule set perfectly maintains the performance of the neural network it was derived from, but yet gives us more explainability and readability. Right? If you look at the first rule, it says if the loan term is more than 12 months and purpose is cash provisioning and savings account is less than 12.40 euro and year's client is less than or equal to 3, then the applicant is considered as a bad payer. So it gives me a clear explanation of why an applicant is considered as bad or good. So if I deny credit to a customer, now I have this interpretation facility readily available and I can tell him or her why credit has been denied. You can see a few more rules like that. So we have a total of 5 rules and we have a default class which says the applicant is good. Obviously, you can have, depending upon the complexity of your neural network, whether it's a shallow or a deep learning one, you will have more or less rules. And if you want to take the interpretability aspect one step further, you can represent it as a decision table. Here you can see a decision table. It's a top-down structure, so you kind of evaluate it in a top-down way. This is a decision table that corresponds to the rule set I just presented. So if savings account is less than or equal to 12.40 euros, then you have to look at economic sector. However, if savings account is bigger than 12.40 euros, then you can see that the applicant is good. This is an example insight that was not that much clear from the rule set I just showed you on my previous slide, right? But it turns out that this rule set corresponds to this very basic insight that if the savings account is bigger than 12.40 in terms of balance, then the applicant is good. Otherwise, we have to look at all these other variables and risk factors like economic sector, purpose of loan, term, years client, etc. So this is one way to make deep learning models interpretable, to extract rules from them and represent them as decision tables. Again, if you want more information on that, in our machine learning course, BlueCourses course on www.bluecourses.com, we carefully explain how you can get those rules using pedagogical and decompositional approaches. Hence, to conclude this very short presentation, it's a bit my perspective. I think we see a lot of buzz these days, deep learning, machine learning, smart learning, and so on. I see a tremendous gap between academic research and business. I mean, one of the gaps that I often identify is that academics overly focus on, for example, accuracy rather than interpretability or profit. Academics sometimes overly focus on estimation times of machine learning models. They want to quickly estimate, and even a couple of milliseconds faster already leads to an academic publication. I think businesses are not interested in that. They don't care how long it takes to estimate a machine learning model. Right? If it takes a few seconds longer, nobody cares. But what they are interested in is to have machine learning models that really add value. Value in terms of accuracy, but also in terms of interpretability, operational efficiency, and at the end of the day, profit. My take on deep learning, it's a useful technology stack, but you have to be very careful with it. We've seen that on structured data, it has no performance benefit. Structured data, remember, is what I refer to as tabular data. The type of data you usually use in applications such as churn prediction, credit scoring, fraud detection, and so on. On unstructured data, I think deep learning has definitely shown its merits. For analyzing image data, for analyzing text data, for analyzing audio data, for analyzing video data, deep learning is needed, right? Because these are really complex, non-tabular based data sources where deep learning has shown that it's really good at. The role of interpretability is very important because of various regulations that have been recently introduced, because of GDPR, the privacy regulation, antitrust laws, Basel, solvency, and so on. So interpretability is very important. In this presentation, I briefly looked upon one type of interpretability, it's rule extraction. Back to the if-then rules, right? The if-then rules that we originally derived from experts, but now from data, using, for example, deep learning methods, which were then turned into interpretable if-then rules using rule extraction techniques. It is my firm belief, and that's a research project that we're currently started working on, that graphical models such as Bayesian networks, which have also been known for ages. I mean, I did my PhD in 2003, and Bayesian networks were already known then. I think that those graphical models, whereby you have your dataset variables being represented as nodes in a network with arrows depicting dependencies or causal relationships between them, those type of models, I think, will become very, very, very important. If you want more information about that, I'm happy to refer to our BlueCourses initiative, where we discuss all of these, what I've discussed in this presentation, into more details, especially in the Machine Learning Essential course. But we're also offering other courses on basic credit risk modeling, advanced credit risk modeling, fraud analytics, and social network analytics. And we have courses coming up on text analytics, deep learning, and uplift modeling. So really hope to see you at BlueCourses.com. We already have a very nice customer portfolio. We have some leading banks like HSBC, Santander, Big Bank. We also have already quite a few companies that sign up for our courses. So hope you enjoyed this presentation, got a few insights from it. As I said, if you want, you can mail me for the slides of it. Happy to share them with you, and hope to meet you at our BlueCourses.com initiative. Thanks very much. Bye-bye.